When scientists cut into the bones of 17 Tyrannosaurus rex specimens in January 2026, they found something that should have been impossible after 66 million years. Growth rings. Dozens per specimen, far more across the entire sample than anyone predicted. For 2 decades, we believed T-Rex reached full size by age 20. The textbooks said so. Museum labels confirmed it. The 2004 Nature study that rewrote paleontology made it scientific fact, but those 17 bones told a different story. They revealed that T-Rex didn't stop growing at 20, or 25, or even 30. These creatures took 40 years to reach full size, twice as long as we thought. And every museum label, every documentary, every textbook, all of it was based on incomplete evidence. I'm going to show you what those bones revealed, how scientists missed this for 20 years, and what it means for everything we thought we knew about the most studied predator in history. This isn't just about adjusting a number. When you change how long an animal takes to grow, you change everything. How it hunted, how it competed, how it raised its young, how many could survive in one ecosystem. When those 17 bones were analyzed at Oklahoma State University in January 2026, they didn't just revise T-Rex biology, they rewrote it. The study was led by paleontologist Holly Woodward, and it represents the largest bone histology analysis ever conducted on Tyrannosaurus rex. 17 specimens, 12 transverse bone sections, hundreds of microscopic growth marks examined under circularly polarized light, a technique that reveals tissue patterns and growth marks that are extremely difficult to see under standard microscopy. The data was unambiguous. T-Rex grew slowly, much more slowly than we thought. Here's what makes this discovery so remarkable. The original 2004 study that established the rapid growth model used 7 specimens. It was groundbreaking work. It gave us our first real understanding of T-Rex life history. But 7 specimens is a small sample. And when Woodward's team expanded that to 17 and applied new microscopy techniques, the picture changed completely. The growth rings in these bones are like tree rings. Each one represents a year of life. But here's the problem: some rings are almost invisible under standard light microscopy. They're called annuli, and they show up much more clearly under circularly polarized light. The 2004 researchers couldn't see many of these rings because the technology wasn't widely available yet. They weren't wrong. They were working with the tools they had. But in 2026, with better tools and more specimens, we can finally see the complete picture. And that picture shows T-Rex living longer, growing slower, and behaving very differently than we imagined. Over the next 25 minutes, we're going to explore this discovery in detail. We'll start with what we used to believe, the foundation built by decades of careful research. Then we'll examine the breakthrough, what those 17 bones revealed and how scientists discovered it. We'll explore the implications, what this means for tyrannosaur behavior, ecology, and evolution. We'll look deeper into the sensory systems that made T-Rex such an effective predator. And finally, we'll consider what this discovery teaches us about science itself, and why rewriting what we know isn't a failure, it's progress. By the end, you'll understand why this single study, published in the peer-reviewed journal PeerJ in January 2026, is being called the most important tyrannosaur research since the original 2004 breakthrough. You'll see how 17 bones changed our understanding of the most famous predator that ever lived. And you'll understand why, even after 120 years of studying Tyrannosaurus rex, we're still discovering the impossible inside its fossils. Let's begin with what we thought we knew. To understand why the 2026 discovery is so significant, we need to go back to what we believed before. And that story begins in 2004, when a team led by Gregory Erickson published a landmark study in the journal Nature. Erickson's research was revolutionary. For the first time, scientists could track how fast T-Rex grew by examining microscopic growth marks in fossilized bones. The technique is called bone histology, and it works like this. You take a fossilized bone, usually a weight-bearing bone like a femur or tibia, and you cut an extremely thin cross-section. Then you examine it under a microscope. The bone tissue shows growth marks just like tree rings. By measuring the spacing between these marks, you can calculate how fast the animal was growing each year. Erickson's team analyzed 7 Tyrannosaurus rex specimens ranging from juveniles to full-grown adults. The smallest specimen they studied weighed about 60 pounds. The largest, a massive adult, weighed around 6 tons. By tracking the growth marks in each specimen, they reconstructed a growth curve showing how T-Rex went from hatchling to apex predator. The results were stunning. T-Rex went through an explosive growth spurt during adolescence, gaining roughly 4.5 pounds per day at its peak. That's approximately 1,700 pounds per year during the fastest growth phase. The animal reached full adult size around 6 to 8 tons by age 20. After that, growth slowed dramatically and the animal reached skeletal maturity. Based on the largest specimens available, Erickson estimated that T-Rex probably lived to about 30 years maximum, with most individuals dying younger. This was a complete revelation. Before 2004, scientists had debated whether dinosaurs grew slowly like modern reptiles or quickly like modern birds. Erickson's study settled the debate. T-Rex grew fast, very fast, faster than any living reptile, though not quite as fast as large mammals like elephants. This rapid growth made sense. In the brutal Cretaceous ecosystem, growing quickly meant reaching a size where you could defend yourself or dominate others. A slow-growing juvenile would be vulnerable for years. The 2004 model became the standard. Many museums updated their exhibits, documentaries featured it, textbooks incorporated it. Major institutions adjusted their T-Rex displays to reflect the new science. The labels next to those massive skeletons told visitors that T-Rex grew up fast and lived hard. There was no reason to doubt it. The research was solid. Erickson's team had used the best techniques available. 7 specimens might seem like a small sample, but T-Rex fossils are rare. Only about 50 reasonably complete specimens have ever been found. Getting access to 7 for destructive sampling, cutting into precious fossils, was a major achievement. The study was peer-reviewed, published in one of the most prestigious scientific journals in the world, and replicated by other researchers. For 20 years, this model held. Other studies added details. Some researchers analyzed different bones. Some looked at related species like Albertosaurus and Gorgosaurus, but the basic picture remained the same. Tyrannosaurus rex was a fast-growing, relatively short-lived predator. It reached full size by its early 20s and probably didn't live much past 30. This wasn't just an academic detail. It shaped how we understood T-Rex behavior. A fast-growing animal needs enormous amounts of food. That meant T-Rex had to be an aggressive, opportunistic hunter taking down prey constantly to fuel its growth. It also meant competition was fierce. With a relatively short lifespan, every year mattered. Juvenile T-Rexes had to grow quickly or they'd be outcompeted by siblings or killed by other predators. It painted a picture of a brutal, high-stakes existence, born into a world where hesitation meant death, growing as fast as biology would allow, reaching dominance in your teens, ruling the late Cretaceous for a decade or two, and then aging quickly, losing your edge and being replaced by the next generation. That was the story we told. That was the science we taught. And in January 2026, 17 bones proved that story was incomplete. The discovery that changed everything began not with new fossils, but with a new look at old ones. Holly Woodward, a paleontologist at Oklahoma State University, had been studying Tyrannosaur growth for years. She was familiar with Erickson's 2004 study and respected it deeply. But she also knew that science advances when you ask questions, even about well-established conclusions. Woodward noticed something interesting. Most growth studies of T-Rex use just 1 or 2 bone sections per specimen. That's standard practice. Bone histology is destructive. You have to cut into the fossil, and museums are understandably protective of their specimens. But Woodward wondered whether a single section was giving us the complete picture. Bones aren't uniform. Growth rates vary along the length of a bone. What if the standard sampling locations were missing something? So Woodward's team did something ambitious. They assembled the largest collection of Tyrannosaurus bone samples ever analyzed. 17 individuals, multiple sections from several specimens, tibiae and femora, the massive weight-bearing leg bones that best reflect overall body growth. Some of these specimens had been studied before. Others were new to histological analysis. Together, they represented the most comprehensive look at T-Rex growth ever attempted. But there was another innovation, the microscopy technique. Traditional bone histology uses standard transmitted light or cross-polarized light. These techniques are excellent for seeing overall bone structure, but they can miss subtle features. Woodward's team used circularly polarized light microscopy. This technique reveals birefringent structures, areas where bone tissue has been remodeled or where growth slowed significantly. Under circularly polarized light, growth marks that are nearly invisible under standard microscopy suddenly become much clearer. When Woodward examined the bone sections under this enhanced lighting, she saw something unexpected. There were far more growth marks than anyone had counted before. Not just the prominent lines of arrested growth, the lags that show up clearly under standard microscopy, but also annuli, fainter bands that represent slower growth periods. Under circularly polarized light, these annuli were much more visible, and there were dozens of them in many specimens. Each growth mark represents a pause or slowdown in growth. In most interpretations, each mark equals 1 year. Count the marks and you count the years. Woodward's team developed 4 different statistical models to account for these growth marks. Some models counted only the most prominent lags. Others included the annuli. The models varied in their details, but they all pointed to the same conclusion. T-Rex grew much more slowly than Erickson's 2004 model suggested. And critically, the growth didn't taper off sharply in the early 20s. It continued slowly but steadily well into the animal's 30s. The growth curves told a new story. Instead of a rapid adolescent growth spurt followed by a quick plateau at age 20, the data showed prolonged steady growth extending to 35 or 40 years of age. The animal didn't hit its maximum size until much later in life. And if growth continued that long, it meant T-Rex probably lived significantly longer than 30 years. Some individuals might have reached 50 years or more. Let's put this in context with specific numbers. The 2004 model estimated that T-Rex reached about 5,500 kilograms, roughly 6 tons, by age 20. Woodward's 2026 analysis suggests that at age 20, T-Rex was still subadult, probably weighing 3,000 to 4,000 kilograms, 3 to 4 tons. Full adult mass of 6,000 to 8,000 kilograms wasn't reached until the mid to late 30s. That's a difference of 15 to 20 years. Why did Erickson's team miss this? They didn't. They made the best interpretation possible with the data available: 7 specimens, standard microscopy, and limited sampling. Those constraints meant some of the fainter growth marks simply weren't as visible. The growth curve they produced was accurate for what they could observe, but it wasn't the complete picture. Science builds on itself. Erickson's 2004 study was a foundation. Woodward's 2026 study expanded that foundation with more specimens and better tools. The data was published in the journal PeerJ in January 2026. The paper is titled "Prolonged Growth and Extended Subadult Development in the Tyrannosaurus rex Species Complex Revealed by Expanded Histological Sampling and Statistical Reanalysis." It's open access, meaning anyone can read it. The supplementary materials include high-resolution images of the bone sections, raw measurements, and statistical models. The team also uploaded their entire dataset to Figshare, an open data repository, so other researchers can verify the results. The scientific community responded quickly. Some paleontologists were skeptical at first. 20 years of consensus doesn't shift easily, but as researchers examined the data and the images, the evidence became compelling. Those previously undetected growth marks were real. The circularly polarized light microscopy wasn't revealing artifacts. It was revealing biology that had been difficult to observe before. Within weeks, major museums began discussing how to update their exhibits. The implications hit immediately. If T-Rex took 40 years to reach full size, then every assumption built on the rapid growth model needed to be reconsidered. How did juveniles survive for decades before reaching dominance? What did subadult T-Rexes eat? How did they avoid competition with adults? And most intriguingly, if T-Rex grew slowly, what about Nanotyrannus? Nanotyrannus is the name given to smaller Tyrannosaur fossils found in the same time and place as T-Rex. For years, paleontologists debated whether Nanotyrannus was a separate species or just a juvenile T-Rex. The rapid growth model supported the juvenile T-Rex interpretation. If T-Rex grew quickly, then smaller specimens were probably just young individuals. But if T-Rex grew slowly and took decades to mature, then those smaller fossils couldn't all be juveniles. Some had to be adults of a different, smaller species. In November 2025, just 2 months before Woodward's study was published, another major discovery emerged. A team analyzing the famous dueling dinosaurs fossil, a Nanotyrannus and Triceratops preserved together, published evidence that Nanotyrannus was indeed a distinct species. The bone histology showed the Nanotyrannus specimen had reached skeletal maturity. It wasn't a juvenile. It was a fully grown adult of a smaller Tyrannosaur species. Suddenly, the late Cretaceous Hell Creek ecosystem looked very different. Not one apex tyrannosaur, but potentially 3, Tyrannosaurus rex, the largest, growing slowly over decades to reach massive size. Nanotyrannus lancensis, a smaller, more agile species reaching maturity faster. And potentially other related species still under study. Multiple tyrannosaurs coexisting, each occupying a slightly different ecological niche. This is how science progresses, not by tearing down old ideas out of spite, but by building on them with new data. Erickson's 2004 study gave us the tools to understand dinosaur growth. Woodward's 2026 study refined that understanding with more specimens and better technology. Both are part of the same story, the story of slowly, carefully, patiently revealing the truth about creatures that died 66 million years ago. But understanding how long T-Rex took to grow is just the beginning. Now we have to ask, what did that slow growth mean for how T-Rex lived? When you change the timeline of an animal's life, you change everything about how that animal fits into its world. A T-Rex that takes 40 years to reach full size is fundamentally different from one that reaches full size at 20. Let's explore what this means. First, consider the juvenile period. Under the old model, a juvenile T-Rex spent maybe 5 to 10 years as a vulnerable subadult before hitting its growth spurt and rapidly reaching dominance. Under the new model, that vulnerable period extends for decades. A 20-year-old T-Rex wasn't a young adult on the verge of dominance. It was a mid-sized subadult, probably weighing 3 to 4 tons, dangerous, but nowhere near its full potential. What did these subadult tyrannosaurs eat? This is where the story gets fascinating. A 3-ton predator can't hunt the same prey as an 8-ton predator. The mechanics don't work. A subadult T-Rex lacked the bone-crushing bite force of an adult. Its skull wasn't fully developed. Its jaw muscles weren't at maximum strength. It couldn't take down a fully grown Triceratops or Edmontosaurus, so it had to hunt differently. This is where Nanotyrannus becomes crucial. If Nanotyrannus was a distinct species, a smaller tyrannosaur reaching maturity at around 1,500 to 2,000 kilograms, then it was competing directly with subadult T-Rex. Both were mid-sized predators hunting mid-sized prey. Both were agile enough to chase down hadrosaurs and juvenile ceratopsians. Both occupied that crucial ecological middle ground between giant apex predators and smaller theropods like Dacataraptor. The Hell Creek Formation, the geological layer where most T-Rex fossils are found, preserves an ecosystem from the last few million years before the asteroid impact. It's one of the most studied fossil deposits in the world, and the predator guild in Hell Creek was remarkably complex. At the top, massive adult Tyrannosaurus rex capable of killing anything that moved. In the middle, subadult T-Rex and adult Nanotyrannus hunting mid-sized prey. At the lower end, smaller theropods and possibly juvenile tyrannosaurs, taking small prey and scavenging. This creates something called niche partitioning, different predators dividing up resources by size, hunting strategy, and prey preference. It's common in modern ecosystems. In Africa, lions, leopards, cheetahs, and hyenas all coexist by hunting different prey in different ways. In Hell Creek, the same principle applied. Adult T-Rex hunted the largest herbivores. Subadult T-Rex and Nanotyrannus hunted mid-sized prey. Smaller predators took what was left. But there's a complication. As T-Rex aged, it moved through ecological niches. A 10-year-old T-Rex might have weighed 1,000 kilograms, roughly the size of a large crocodile. It was probably hunting small ornithischians and scavenging. A 20-year-old might have weighed 3,000 kilograms. Now it's competing directly with Nanotyrannus for mid-sized prey. A 30-year-old, approaching 6,000 kilograms, was transitioning into apex predator status. And a 40-year-old at full size was the undisputed king. This means T-Rex changed its hunting strategy multiple times throughout its life. Juveniles were pursuit predators, fast, agile, chasing down smaller prey. Subadults were ambush hunters, powerful enough to kill but not yet bulky enough to rely solely on strength. Adults were power hunters, using sheer mass and bite force to dominate. This kind of ontogenetic niche shifting is seen in modern crocodiles, which change from insect eaters to fish eaters to apex predators as they grow. But in T-Rex, it happened over 4 decades. Now consider reproduction. Under the old model, T-Rex reached sexual maturity quickly, probably by age 15 or 16, and started reproducing almost immediately. Under the new model, sexual maturity may have occurred somewhat later. That's a significant difference. A longer time to reproductive maturity means lower population turnover, fewer generations per century, slower evolutionary change. It also raises questions about parenting. If T-Rex took decades to mature, then juveniles might have stayed near parents, or at least in similar territories for extended periods. Modern crocodiles guard their nests and protect hatchlings for a few months, but some large mammals like elephants have extended family structures lasting years. Could T-Rex have had something similar? We don't have direct evidence, but the long maturation period opens the possibility. Then there's competition between generations. In the rapid growth model, adults and juveniles didn't compete much because juveniles quickly grew into adults, but with a 40-year growth period, there would have been constant competition between subadults and adults. A 35-year-old T-Rex nearing full size would have been competing with 45-year-olds for territory and prey. This creates intense selective pressure. Only the most successful individuals, those that secured the best hunting grounds, avoided injury, and outlasted rivals, would have reached maximum size. The fossil record hints at this. Many T-Rex specimens show evidence of healed injuries, broken ribs, bite marks on the skull, infections. Some of these injuries were likely from hunting accidents, but some were almost certainly from fights with other tyrannosaurs. Tooth marks matching T-Rex dentition have been found on T-Rex bones. These animals fought each other, and if they took 40 years to reach dominance, those fights would have been a constant feature of their lives. There's another implication: lifespan. If T-Rex didn't reach full size until 40, how much longer did it live? The 2004 model suggested most T-Rexes died by 30. The 2026 model suggests that 30 was barely past middle age. Some individuals might have lived to 50, 60, or even older. We don't know the maximum lifespan yet. The bone histology shows continued slow growth even in the largest specimens, which suggests they were still alive and growing when they died. But whether they died from old age, disease, injury, or bad luck, we can't say for certain. This potential longevity has interesting implications for behavior. Long-lived animals often develop more complex behaviors. They have more time to learn. They benefit from experience. Modern elephants, orcas, and great apes all have extended lifespans and sophisticated social behaviors. If T-Rex lived for decades, it had time to learn its environment, remember the locations of prey, recognize rival individuals, and develop refined hunting strategies. A 40-year-old T-Rex that had been hunting the same river valley for 3 decades would have known every trail, every crossing, every ambush point. This brings us to one of the most exciting aspects of the new model. It makes T-Rex more interesting. The old model painted T-Rex as a hyper-aggressive, fast-living predator, terrifying but almost mechanical in its simplicity. The new model shows an animal with a complex life history, decades of growth, changing hunting strategies, competition with rivals, learning and adaptation. This is an animal that lived a long, eventful life in one of the most competitive ecosystems that ever existed. And there's one more implication we need to consider. If T-Rex took 40 years to mature, then the famous T-Rex specimens we know, Sue, Scotty, Stan, Trix, weren't just big, they were survivors. These were animals that had survived for 4 decades in a world designed to kill them. They'd outlived countless rivals, avoided disease, healed from injuries, and finally reached the size where nothing could challenge them. That makes those fossils even more remarkable. When you stand next to Sue at the Field Museum in Chicago, you're not just looking at a big dinosaur. You're looking at an individual that beat the odds for 40 years and reached the top of the food chain. That skeleton represents a lifetime of experience, competition, and adaptation. And now, thanks to 17 bones examined under circularly polarized light, we finally understand just how long that lifetime was. But size and longevity aren't the only things that made T-Rex a supreme predator. We need to talk about its senses, because the same fossils that revealed its growth also revealed something extraordinary about how it perceived its world. If you want to understand what made Tyrannosaurus rex so successful, you can't just look at its size. You have to look at its brain. And here, the fossil record offers something remarkable, preserved brain cases that show us exactly how T-Rex perceived the world. When a dinosaur dies and fossilizes, the brain itself decays. But the brain case, the bony cavity inside the skull that houses the brain, remains. And because the brain fits snugly against the skull, the interior surface of the brain case preserves an impression of the brain's shape. Paleontologists can create digital casts of these brain cases using CT scanning. These casts, called endocasts, show the size and shape of different brain regions. They're not perfect, they show the outline of the brain, not its internal structure. But they tell us a tremendous amount about sensory capabilities. T-Rex endocasts reveal something astonishing. This animal had one of the most sophisticated sensory systems of any predator in the Mesozoic. Let's start with vision. The orbits, eye sockets, in a T-Rex skull face forward. That's unusual for dinosaurs. Most dinosaurs, like most modern reptiles and birds, have laterally placed eyes that provide a wide field of view. Forward-facing eyes reduce the total field of view but create something much more valuable: stereoscopic vision. Stereoscopic vision means the visual fields of the two eyes overlap. Your brain combines the slightly different images from each eye to create depth perception. This is crucial for predators. Judging distance accurately means knowing exactly when to strike. Miss by 6 inches and your prey escapes. Forward-facing eyes give that precision. T-Rex had significant binocular overlap, excellent for a terrestrial predator and comparable to modern hawks. But there's more. The size of the orbit tells us about eye size, and eye size correlates with visual capability. T-Rex had enormous eyes, some of the largest of any land animal. Large eyes gather more light and can have more photoreceptor cells, which means better resolution. Based on orbit size, T-Rex probably had very high visual acuity for a terrestrial predator. It could spot prey from considerable distances. And with depth perception to match, it could judge exactly how far away that prey was. Now combine that vision with the sense of smell. The olfactory bulbs, the parts of the brain that process smell, are visible in T-Rex endocasts, and they're massive. Proportionally, T-Rex had larger olfactory bulbs than almost any other dinosaur. In modern animals, olfactory bulb size correlates closely with olfactory capability. Dogs, with their legendary sense of smell, have large olfactory bulbs relative to body size. T-Rex had olfactory bulbs comparable to modern vultures and bloodhounds. What does a powerful sense of smell give you? The ability to detect prey you can't see, to track wounded animals across miles, to locate carcasses from great distances, to identify rival individuals by scent. Smell is particularly useful in dense vegetation at night or over long distances, all situations where vision is limited. A T-Rex could probably smell a hadrosaur herd from miles away. It could track a bleeding triceratops for considerable distances. It could detect a dead sauropod from across an entire river valley. Now combine vision and smell with hearing. The inner ear structure, also visible in endocasts, tells us about hearing sensitivity. T-Rex had a well-developed cochlea and large semicircular canals. This suggests good low-frequency hearing. Low-frequency sounds travel farther than high-frequency sounds, especially through dense vegetation. Many large modern predators, like lions and crocodiles, use low-frequency vocalizations to communicate over distance. T-Rex likely did something similar. That means it could hear the sounds of a hadrosaur herd before it could see them. It could detect the distress calls of wounded prey. And it could likely communicate with other tyrannosaurs using low-frequency calls that traveled long distances. What you have here is an integrated sensory system. Not just good vision or good smell, but both plus hearing all working together. This is the hallmark of an apex predator. Modern wolves hunt by combining vision, hearing, and smell. Great white sharks integrate vision, smell, and electroreception. T-Rex did something similar, using every available sense to locate, track, and kill prey. There's one more aspect we need to consider: intelligence. This is tricky. Brain size doesn't directly equal intelligence, and endocasts don't tell us about neuron density or brain chemistry, but we can make some reasonable inferences. T-Rex had a brain size typical for large theropods, likely comparable to modern crocodiles in terms of overall neural capacity. Crocodiles are surprisingly capable. They can learn, remember, and adapt their behavior. If T-Rex had similar capabilities combined with a 40-year lifespan and those extraordinary senses, it would have been highly effective at learning from experience. A 40-year-old T-Rex wouldn't just be bigger than a 20-year-old. It would be more experienced, better at predicting prey behavior, more skilled at avoiding injury, more knowledgeable about its territory. Imagine a hunting scenario. A T-Rex spots a hadrosaur herd in the distance, visual detection. It moves downwind to avoid being scented, behavioral adaptation. It uses smell to identify individuals, perhaps detecting an old or injured animal. It listens for sounds that might indicate which animal is moving differently. Then it uses its depth perception to judge exactly when to charge. And finally, it uses decades of experience to predict where the herd will run and position itself accordingly. That's not a mindless eating machine. That's an intelligent, experienced predator using every tool available, and the fossils prove it had those tools. The endocasts show the brain structure. The bone histology shows the lifespan. The skull anatomy shows the senses. All of it comes together to paint a picture of an animal superbly adapted to its role. This is what the 2026 discoveries revealed, not just that T-Rex grew slowly, but that its entire life history was more complex than we imagined. Long-lived, slowly maturing, sensorially sophisticated, and behaviorally flexible. Not a simple brute, but an apex predator refined by millions of years of evolution to dominate one of the most competitive ecosystems in Earth's history. 66 million years ago, at the end of the Cretaceous period, an asteroid roughly 10 kilometers wide struck the Gulf of Mexico. The impact released energy equivalent to billions of nuclear weapons. It vaporized rock, sent superheated debris into the stratosphere, triggered global wildfires, and blocked out the sun for years. In the aftermath, approximately 75% of all species on Earth went extinct, including every non-avian dinosaur. Tyrannosaurus rex, the apex predator of its ecosystem, died with them. Not because it was poorly adapted. The 2026 research proves exactly the opposite. T-Rex was one of the most successful predators in Earth's history. Sophisticated senses, long lifespan, complex behavior, flexible hunting strategies. It was perfectly adapted to the late Cretaceous world. But when that world ended, adaptation didn't matter. The food chains collapsed. The herbivores starved. And the predators followed. There's something humbling about that. All that evolutionary refinement, millions of years perfecting bone structure, sensory systems, life history ended catastrophically. Not because T-Rex failed, but because the environment changed faster than evolution could respond. The ancestors of modern birds survived the asteroid impact not because they were better than T-Rex, but because they were small, adaptable, and able to survive on scarce resources. Size and power were liabilities in the post-impact world. But here's the remarkable part. 66 million years later, we can still study T-Rex. We can cut into its fossilized bones and see growth rings laid down year by year. We can scan its skull and map its brain. We can measure its bite force, estimate its speed, track its injuries, and reconstruct its life history. Science gives us a window into deep time. Those 17 bones analyzed in January 2026 are messages from the Cretaceous, preserved in stone, waiting for someone with the right tools to read them. And we're still learning to read them better. In the 1990s, CT scanning revolutionized our understanding of dinosaur anatomy. In the 2000s, bone histology revealed growth patterns. In the 2020s, circularly polarized light microscopy showed us details nearly impossible to see before. What will the coming decades reveal? We don't know. But the fossils are still there, still waiting, still holding secrets we haven't learned to see yet. This is why the 2026 discovery matters. Not just because it changed what we know about T-Rex, but because it shows how science works. Science isn't about having all the answers, it's about asking better questions. Ericsson's 2004 study asked how fast T-Rex grew. Woodward's 2026 study asked whether we'd measured that growth accurately. Neither was wrong, both were right for the data available, but by questioning, testing, and refining, we moved closer to the truth. And the truth is this: Tyrannosaurus rex was even more remarkable than we thought. Not a simple predator that grew fast and died young, but a complex, long-lived animal that spent decades mastering its world. An animal that changed hunting strategies as it aged. that competed with rivals for territory and prey, that used sophisticated senses to track and kill, that survived in one of the most dangerous ecosystems imaginable for 40 years or more before reaching its full potential. Those 17 bones didn't just rewrite T-Rex biology. They gave us a window into a life. A 40-year journey from hatchling to apex predator lived 66 million years ago in what's now Montana, North Dakota, and South Dakota. And they reminded us that even the most famous, most studied, most iconic animal in paleontology still has secrets to reveal. So the next time you visit a natural history museum and stand next to a T-Rex skeleton, remember this. You're not looking at a monster from a movie. You're looking at the fossilized remains of a real animal that lived a long, complex life. An animal that hunted and competed and survived for decades. An animal that saw sunrises over Cretaceous floodplains and heard the calls of hadrosaurs echoing through ancient forests. An animal whose bones, buried for 66 million years, still have new stories to tell. And thanks to 17 of those bones, examined in January 2026 with tools that didn't exist 20 years ago, we finally understand that one of those stories, the story of how long it took to become the king of dinosaurs, wasn't 20 years. It was 40.